Hi everybody, welcome back to Multirate Signal Processing. Today about non-ideal filters. So we saw that we can get perfect reconstruction in a filter bank using ideal filters. Ideally we remove all alias components in this way. But in practice we don't have ideal filters. They are not realizable because their impulse response stretches from -infinity to infinity, like in the sing function. How do we obtain perfect reconstruction using realizable non-ideal filters and still critical sampling, meaning the downsampling rate N is equal to the number of subbands as in the case of ideal filters? So that's important, for instance, for compression, where we don't want to increase the number of samples because we want to reduce the data rate. Let's first take a look at the resulting spectrum when we have non-ideal filters. We start with a spectrum at the output of a non-ideal high pass as in the example last time. So here we can see the spectrum. Here it goes from -pi to +pi, so positive and negative frequencies. We assume a real valued filter impulse response, and hence we get this symmetry between positive and negative frequencies here. And we can see we have a filter which is an example here. So we have a passband which goes down a little towards pi, and then we have this non-ideal part which is in the transition region between passing and stopping. So it's not stopping immediately in the low frequency region as it should be for an ideal filter, but we have a transition here from passing to stopping as the case for any realizable filter. So observe that we have the slope at pi/2 and -pi/2, which is not infinite, but we get a more or less slow transition into higher attenuation towards lower frequencies. Hence, we also get frequencies below pi/2 or above -pi/2 in our signal. This will become a problem after downsampling by a factor of 2. For now, just the multiplication with the delta impulse train, as can be seen in the next pictures. Remember that for the multiplication with the delta train, we get aliasing components at frequency shifts of 2π/N, hence in this case pi. So here we can see the resulting spectrum after sampling of our high-pass signal. So here we can see the original piece. Here's the original, and then this is shifted towards the low-frequency positive region, and then this piece is shifted towards the negative low-frequency region. And we can see here these triangles, these are the alias components. So now we have an overlap between this alias component, the spectral copy, and the original frequency region. So if you just have this high pass, then this part of our spectrum would be destroyed. We cannot recover it. But in filter banks, we have also the low pass, the low frequency region. And since this low frequency region also contains the frequency which is aliased here, we have the hope that we can recover it using a filter bank. So observe, even if we now used ideal filters for the synthesis for the high pass part, we would still have to have the overlapped alias component and hence no perfect reconstruction. Right? And this leads us to filter banks. So hopefully with filter banks we can get rid of all those aliasing components coming from realizable filters. Filter banks consist of a bank of subband filters which cover the entire frequency band of our signal, followed by downsampling in the analysis filter bank, and preceded by upsampling in the synthesis filter bank. This can be seen in the following pictures. So here we have the analysis filter bank. So here in the beginning we have a low pass, then we have a sequence of band passes, and finally we have a high pass here. And each is followed by a downsampler by a factor of N. And then we have our output signals at the lower sampling rate, downsampled by this factor of capital N. So we have, in total, we have the same number of samples, but instead of a high sampling rate time signal, we have now several low sampling rate subband signal. Yeah, and then the synthesis filter bank is able to recover the original high sampling rate audio signal from those several low sampling rate subband signals. So the first step of the synthesis filter bank is the upsampling here, which recovers the original sampling rate by inserting capital N-1 zeros after each sample. And then we have the reconstruction filter or interpolation filters here, which basically fishes out the correct spectrum. So here this would be a low pass filter, and in the end you would have a high pass filter here, and then in between you would have corresponding band pass filters, each suppressing the unwanted spectral copies. And then you add up all those spectral band pass signals to get a full spectrum, full sampling rate audio signal back. Yeah, so in the picture, x of n is the input signal, for instance our audio signal, yk of m are the downsample subband signals, with k the subband index and m the index at the lower sampling rate. And x hat, after the synthesis filter bank, is the reconstructed signal. As described in lecture 2, where we defined the notation, down arrow capital N symbolizes downsampling by a factor of capital N, including the removal of the zeros. And if x of n is the signal we downsample, then we also write the downsample signals as x subscript n naught, down arrow capital N of m is defined as every nth sample of x with a phase offset of n naught. Right? So we start downsampling at sample n naught. So we could start at sample number 0, the first sample, but we don't have to. We have the choice. We can also start with the first, the second, and so on. So n naught is the index of the first sample we keep in the downsampling, or the phase. We also call it the phase. And this n naught can accordingly between 0 and capital N-1. Right? So up arrow capital N symbolizes the upsampling by a factor of capital N, including insertion of the zeros. If y of m is the signal we upsample, then we also write the upsample signal as this. So we have y of subscript n naught. N naught is again our phase index. Then we have this up arrow capital N here in the superscript of n is defined as every capital nth sample starting with the phase index n naught has our sample y of m, and in between we have zeros. Right? So again, n naught is the index of the first non-zero sample in the upsample signal, or the phase, with again n naught between 0 and capital N-1. So n naught would be the index of the first non-zero entry, and then every capital nth sample again contains a non-zero sample. It can be 0, but it's part of the signal, and in between we have all zeros. The analysis can be found, for instance, in audio encoders, where we do the decomposition into subbands, and the synthesis in the audio decoders, where we reconstruct the original audio signal. We would like to have the subband decomposition of our signal, because in this way we can process each subband signal differently, for instance according to the different sensitivities of our ear at different frequencies. We can obtain the different subband filters of our filter bank, for instance by using our window method and modulation. Remember, using modulation we can turn a low-pass filter into a band-pass filter or a high-pass filter. And the modulation frequency gives the center frequency of our resulting filter. So that's very convenient for building subband filters for filter banks. So our goal here is perfect reconstruction, because we want to have the best possible audio reconstruction in coding, which means the output signal is identical to the input signal except for some delay d. So here, mathematically, x hat of n is identical to x of n minus d with this delay d. And of course, for a good decomposition, we also need good frequency responses, meaning high stop-band attenuation. So the only hope we have to obtain perfect reconstruction with non-ideal filters and still critical sampling in filter banks is that somehow the aliasing from different subbands cancels out during the synthesis process when we add up all the subbands. If we add, for instance, a low-pass signal and the high-pass signal for the reconstruction. So both have alias in the neighboring regions, and we could construct our filter banks such that the aliasing then cancels. If they have opposite signs, then they would cancel. Or in other words, we would like the sum of all aliasing components at the output of the synthesis filters to become 0. Right? If we have some components plus, others are minus, then they cancel. The question now is, how do we obtain this goal? So this sounds rather difficult because we have so many alias components. It's actually not just between neighboring subbands, but basically it can be between any subbands because the filters have a finite attenuations. So we could now analyze all the aliasing components to find out when they cancel each other. This is actually how researchers approached this problem first, for instance, in the first derivation of the so-called time domain aliasing cancellation, TDAC filter banks by Princeton and Bradley. Here I have a link to one of their early papers at ICASP. And I'm just seeing the year is missing. It's in the 80s, 84 or something. Or using the aliasing component matrices by Wetterly et al. But it turned out that a simpler mathematical approach is possible by just using the goal of overall perfect reconstruction of our filter bank, regardless of all aliasing components. This is now the goal of the following derivation. Here we need to analyze in more detail what happens in the filtering and downsampling process in our filter bank. So to come to a solution, we need to apply the Z-transform to our filter bank with non-ideal filters. So now we can use the toolbox of the Z-transform domain properties from last time to obtain filter banks with perfect reconstruction and non-ideal filters. So again, here we have our analysis filter bank. And now we go into the math. So the filtering can be written with a convolution. Here you have the convolution equation. We have the filtering, x, the input, convolved with hk, the kth subband filter, and this is the corresponding filtered output before downsampling. The filtering and subsequent downsampling by N of the kth analysis filter hkn of impulse response length L can be written as a downsampled convolution sum with phase offset n0 for generalizability, simply with a substitution mn plus n0 is replacing n prime. Right, so here we go to this equation. N prime is the index that we want to downsample, and we simply only compute every nth value of it, starting with sample n0. So we can do that by using this index substitution. Yeah, so Then we can also give y a new argument at the lower sampling rate. So lowercase m signifies the lower sampling rate. So then we get to this new equation number 2 here. You can see it's basically the same convolution equation, but we replaced n prime by m times capital N plus n naught here. And here we just have this lowercase m for convenience on the left hand side. Yeah, so this is also the notation that I introduced in lecture 1. So m is again the downsampled index at the lower sampling rate, and n naught is our phase index for the downsampling. Often we assume n naught equals 0, which means we start downsampling at the first sample with keeping the first sample. In this way, the sum only computes the values which the downsampler actually keeps. The downsampling in this equation is now the hurdle to simply applying the z-transform to turn the convolution into a multiplication for easy invertibility. Right? Remember, the z-transform had the big advantage that a mathematical complicated operation like the convolution was turned into a mathematically much easier operation like multiplication. And for multiplication, we have easy invertibility, which in the end we want for perfect reconstruction. Right? So now the goal is to somehow find out how to do it with a downsampled version. And for that, we first look at block transforms. Block transforms we saw as, for instance, the DFT. So to look for a solution for invertibility, perfect reconstruction at Elias cancellation, we now take a detour to fast implementations using transforms like the DFT and its fast implementation, the FFT. This is also the approach used by the short time Fourier transform, STFT. So the approach here is we divide our signal into blocks of length n. So then instead of having individual samples, we have a sequence of blocks of length n containing capital N samples each. And then the block index lowercase m is already at the correct lower sampling rate. So if you downsample by a factor of n, then this block sequence already has the correct lower sampling rate in lowercase n. Right? So we start with the first block of n samples, and this gets the first index, number 0. Then we take the second block of our signal, taking the next capital N samples, that gets the index m equals 1, then the next gets m equals 2, and so on. So quite simple. Instead of samples, we now process blocks. And we can also rewrite it in terms of downsampling. When you look at each entry of the sequence of the blocks, we have a downsample sequence. So we have lowercase m times capital N, and we have different offsets. Right? Here we have offset 0 in the beginning, then we have offset 1 or phase 1 up to phase n minus 1. So each entry here in this sequence can be seen as a downsampled sequence of our original signal, started at different phases or different offsets. So here offset 0, phase 0, here offset n minus 1. So this is then the n naught. Right? Each is downsampled by capital N, but starts at different indices. So this is showing two different viewpoints. So the first equation here is the viewpoint of viewing the signal as a sequence of blocks. The second entry here is viewing the signal as different downsampled versions with different phases and not. Right, depending on which way you look. So here you look along the downsample index, the time axis. Here you look along the block interior, sort of. So M is the block index, or index at the lower sampling rate. You can imagine the signal as a long horizontal sequence of samples, which we subdivide into small blocks of length capital N. We then stack those blocks on top of each other. Then going vertically down, we obtain downsampled versions of our signal at different phase lags. So you can see it here. Just 4 samples, 2 blocks. Here capital N would be 2. So here we have the first block. Here we have the second block in the row below. So this would be a sequence of blocks then. But when we look at the first column here going down, we have a downsampled version of X by capital N equals 2, starting at phase 0. And the second column would be phase number 1. The first row would be block number 0. Then the next row, block number 1, would be the next block. Yeah, so the second row is the next block. The rows are the blocks, the columns are the downsampled versions. Yeah, and these are the 2 viewpoints, depending on if you look vertically along the columns, you get the downsampled versions at different phases. If you look horizontally along the rows, you get the different blocks. Yeah, so the DFT computes a block with n frequency or subband values for each signal block X of M. So for each row, we then apply the DFT. If T is the DFT transform matrix, then the DFT of each block is Y of M equals X of M times T. Right, so quite simple. We would apply the DFT to each row, each block, and get the result, which then replaces the original. So Y of M then contains the DFT coefficients. So M again the block index, but now the vector Y now contains the results of the DFT. And now we can see the indices here are no longer phase indices, but now they are subband indices. So we turned the phase indices into subband indices by applying the DFT. So here Yk of M is the kth DFT coefficient for block M. Hence index k denotes this subband or frequency. And index m, lowercase m, is the block index or time at the lower sampling rate. Hence, if we keep k fixed, the subband, we obtain a time signal for the kth subband. So here we would go down along the column, and then we would read out the kth subband along the downsampled time. If we keep m fixed, so the time, we obtain a spectrum for block M. So then we would go horizontally through the different frequency indices or frequency subbands. And this is also why this is called a time frequency representation, since we have both time M and frequency K indices in it. This shows that the DFT is simply a special case of an analysis filter bank with critical sampling and perfect reconstruction through the inverse DFT. Yeah, so DFT, or in this case, you could also say it's a short time Fourier transform. Yeah, so here's a Python example, Pyrex spec waterfall. So here basically we see again a waterfall spectrum. And this basically does this short time Fourier transform on the blocks, or the DFT on the blocks. So here I'm taking a signal from the audio card, subdivide it into blocks, compute the DFT, and then represent each DFT magnitude as a color, which I display on this waterfall spectrogram. So let me open this program first, copy, so gedit, let me increase the size here to make it more easy visible. I'm taking editor gedit, paste, and this is what's inside. So here we have a block size of 2048 samples. This is my variable chunk. From the audio card we get 2 bytes per sample, and I set the sampling rate to 48 kilohertz. Then here I'm opening the audio card using PyAudio. I'm assigning the pointer to A, to P, and then I open this the audio card here in this line and assigning stream the stream from the audio card, and I'm here initializing with the coefficients that I just defined. Here I'm initializing the spectral waterfall, this graphical display. It has 500 rows. The rows now correspond to our blocks. Each row is a block. Columns here is 512. This is the number of subbands which I display here on the screen, and you can see this 512 is less than the block size, and that's simply because of more easy displaying here. Yeah, so the FFT length I'm applying here is 2 times the columns. So you can see the FFT length here will be 1024, and I use double the length of the columns because the upper half is the negative frequencies, and we know it's symmetric. So we can see the FFT length is only half as long as the chunk size, and again this is for speeding up the program so that it also runs on slow computers. Yeah, so that means I miss half the samples, but that's something I can do here because it's just for visualization and not for reconstruction. Yeah, here I have my infinite loop where it continuously reads from the sound card chunk samples, 2048 samples, and then it takes those 2 byte integers and turns it into NumPy integers. Here, or actually floats. So it turns it into NumPy floats. So samples is now an array which consists of float values, which I can now process using the FFT. So here I can now see the displaying. Here I can actually set how many frames I wait before I redisplay it. That's also useful for slow computers. Then you can set it to 2 or 3 to speed it up. Here my computer is fast enough, so I display every frame. Yeah, and here you can see the first frame is assigned by the old frames shifted 1 up. So here you can see here the lower rows get assigned the rows 1 up. Right, this starts at row number 1 and it gets assigned the lower rows, so this is actually the shift up. Now we compute the FFT of our samples, the array of floats, and I'm applying my FFT here of FFT length, so I'm not taking all the samples but only the first half of our array, and I'm keeping only the first half of the FFT output because that contains the positive frequencies. Here I'm doing some normalization and I'm having a factor here, and this will be the red component. Yeah, and I'm also applying the magnitude and the log such that we get a dB-like scale here. So here the third index of 2 means the red component, so R is assigned to the red component. Then the next one is the green component, and I apply this simple nonlinear function to get this colorful display, and here blue gets 1 minus R, So again, this is just for obtaining different colors, and it turns out when it's bright red, then it's the largest magnitude, and if it's bluish, then it's the lowest magnitude. So if R is very small, then blue is very large, and we get a bluish output. Yeah, and we simply continue to do this until wait key finds that I pressed the key Q. Yeah, so let me just do it, execute it. -3. So now you can see here this window. So each row is a spectrum from the DFT, coming from the DFT, and the color is the magnitude of each component. So here we have 512 subband values in each row, and the magnitude of each value, of each subband value, is symbolized by the color. So if we have something yellowish, then it's large. If it's bluish, then it's low. And you can see here left we have the lowest frequencies, we have the highest magnitude, because that's usually the case for audio signals. So here you can see my voice, and you can see my voice here consists mostly of low frequencies, and towards the high frequencies it decays. I can also do whistling. So then this line tells you where my whistling frequency is. So here high pitch, then here low pitch. And you can see when you go up, it's earlier times. So this is a typical time frequency decomposition. So horizontally we have frequency, vertically we have downsampled time, right? So this is the block index. That's why vertically we have the downsampled time, in this case downsampled by the factor of 2048. Right. So this is an easy example of a time frequency decomposition, and if the FFT would be as big as my block size, then we could actually easily invert this time frequency decomposition by applying the inverse DFT. That's the advantage of having the DFT. We also have an inverse. And we already know that the DFT is basically a filter bank with pretty bad filters, so we have a lot of aliasing. And this shows it's actually possible to get perfect reconstruction despite the strong alias components. So let me press the key Q. So now we finished. So this works. And it even has a fast implementation. So you saw that I used the FFT for the DFT, the fast Fourier transform, and that actually allowed me to do it in real time. As fast as the sample blocks arrived, I could compute the FFT and display. So that's an important property, that the DFT can be implemented fast. So has a fast implementation. Compared to our filter bank, per subband we need to calculate the convolution sum. If we have filters of length L, that means we have L multiplications per output sample. We neglect the sum operations here for each subband. Without downsampler, we get L times N multiplications for each block of N input samples for each subband, leading to L n square multiplication for all subbands of the block of N input samples. Now we can reduce this amount by only computing the output samples which the downsampler keeps. This reduces the computational complexity by a factor of N, resulting in Ln multiplications for each input block of length N to obtain n output values, which means we have one value in each subband. In other words, each sample in a subband is computed by a filter of length L, which means L multiplications in the convolution sum. We need L multiplications per sample. If you compare it with an FFT, it only needs on the order of n times log n, or log base 2 of n multiplications, order meaning up to a fixed factor. And that's why it doesn't really matter to which base this log is, because this is what, if we have a different log, this means just a different factor. Hence, for each subband sample, we need log n multiplications. Compare this with the L multiplications per sample for the critical sampled filter bank. So since usually we have the filter length capital L is larger than log of capital N, this is more efficient. But then again, it depends on the number of subbands, right? For instance, if capital N is 1024, then this log 2 of capital N would be 10. And if you have 1024 filters, then usually your impulse response is much longer than this capital N. So for 1024 subbands, this might be 2048. And you see 2048, L equals 2048, is indeed much larger than 10, which is the log of capital N. Right? So that's this example here. If we have 1024 subbands, then we need filters which are longer than this. And that means we have L is much larger than log of 10,040, which is 10. So in this case, we save more than an order of a factor of 100 in complexity using the FFT. And that's actually a big advantage. So it can be a difference between realizable and not realizable. Another interesting effect is that we obtain perfect reconstruction using the inverse FFT for the synthesis process, even though the equivalent FFT filter bank has no perfect filters. So this might give us a hint on how to obtain perfect reconstruction without ideal filters. The question is, what is the equivalent FFT filter bank? Yeah, so that continues then in the next set of slides. So for now, thanks for your attention and see you then in the next set.